Rest your hand on the table. Somewhere inside it, a particle is doing exactly what a particle in a stranger's hand is doing on the other side of the world. Not almost, not approximately, but perfectly, to the 12th decimal place and beyond. Nothing else in nature repeats itself so flawlessly. Why? To answer that, we need three things: a phone call between two physicists, a particle that swims backward through time, and a number measured so precisely it frightens people. Stepping close. Start with the hand on the table, because the entire mystery is already sitting there, hiding inside the most ordinary object you own. Your hand is made of atoms, and wrapped around every atom is a cloud of electrons. The table has its own electrons, so does the coffee in your cup, the coins in your pocket, the air between your face and this screen. Nothing about that is surprising. What should stop you cold is this: every single one of those electrons is exactly the same. Not similar the way two grains of sand are similar, or two snowflakes, or two identical twins. The same in every property nature allows us to measure, to every decimal place we have ever been able to reach. Think about how strange that is compared to everything else you know. No two leaves on a tree match, no two fingerprints, no two stars. Even manufactured things betray themselves under a microscope. Two ball bearings from the same factory, made on the same machine, 1 minute apart, differ in 1,000 microscopic ways. The philosopher Gottfried Leibniz built an entire principle out of this, centuries ago. No two things in nature are perfectly alike. Find two things that seem identical, look closer, and differences appear. It held for leaves, for snowflakes, for everything anyone had ever examined. Electrons break Leibniz's rule. Look closer and the differences never come. Look 1,000 times closer, 1,000,000, 1,000,000,000,000. The electrons in your hand, in the table, in a stranger's hand across the planet, in a star on the far side of the galaxy, every measurement says they are not merely siblings from the same mold. They are indistinguishable in a way nothing in ordinary life prepares you for. And before we go anywhere else, I want you to feel the size of the crowd we are talking about. The observable universe contains roughly 10 to the 80th power electrons, a 9 followed by 79 digits, a number so large that every grain of sand on every beach on Earth, multiplied by itself, does not begin to approach it. 10 to the 80th separate things. And as far as physics can tell, they are all perfectly, exactly, eerily the same thing repeated. That is the mystery sitting under your hand right now. Not a subtle mystery for specialists, a blunt one. When a factory turns out identical parts, there is a mold somewhere, a template, a single original that explains the sameness. What is the mold for electrons? What could possibly force 10 to the 80th objects, scattered across billions of light years, to agree with each other to the last decimal? Hold that question, because in the spring of 1940, one physicist thought he had the answer, and it is one of the most audacious ideas ever spoken aloud in the history of science. It arrived by telephone at Princeton, and the man on the receiving end never forgot a word of it. But to understand what was said in that phone call, and why half of it turned out to be treasure, you first need to see just how deep the sameness goes. Because identical is easy to say. Physics has spent 70 years turning it into the most precisely tested statement in the history of measurement, and the story of how is worth a few minutes on its own. Picture a single electron. Not a cloud of them, not a current, one individual electron, alone. For most of scientific history, that sentence was a fantasy. Electrons came in floods, or not at all. Asking to study one was like asking to study one particular water molecule in a waterfall. Then, in 1973, a physicist named Hans Dehmelt at the University of Washington did something nobody had done before. He caught one. The cage he built is called a penning trap, and it is a beautiful piece of thinking. You cannot grab an electron with tweezers, it is far too small, and it would slip through any material wall as if the wall were fog. But an electron carries electric charge, and charge answers to fields. So Dehmelt built a trap out of nothing, a precisely shaped electric field to hold the particle in place along one direction, and a strong magnetic field to bend its escape routes into tight circles in the others. The electron falls into the middle and cannot leave. It sits there, suspended in a vacuum harder than the space between planets, held by invisible walls circling a few millimeters of emptiness. Dehmelt was so taken with what he had made that he gave it a name, as if it were a new atom. He called it geonium, an atom whose nucleus is not a nucleus at all but the Earth itself, because the electron is bound through the trap's fields to the planet. One particle, alone in its bottle, bound to a world. He kept individual electrons suspended for weeks and months at a time. He gave one of them a name, a single electron, studied so long it earned one. The physical conditions inside that bottle deserve a moment, because they are the quietest place in the known universe. The trap sits in a vacuum better than the space between the planets. At 4 degrees above absolute zero, the residual gas freezes to the walls until collisions essentially stop happening. The magnetic field holding the electron's orbits is 5 Tesla, 100,000 times the Earth's field, steady to exquisite tolerance. The electrodes that shape the electric field are hyperbolic surfaces machined to the geometry the mathematics demands, 8 millimeters apart. Inside that stillness, the electron does 2 things at once. It circles in the magnetic field about 140 billion times per second, and its internal magnetic axis wobbles at a slightly different rate. The entire experiment comes down to comparing those 2 rates. The difference between them is the tiny excess magnetism that theory must predict and the trap must measure, and the electron, circling patiently in its silent bottle, reports it for as long as you care to listen. When the Nobel Committee finally called Seattle in October of 1989, Dehmelt's response entered the small anthology of perfect laureate reactions. "I'm elated," he said. "I wish to dance." A man who had spent 30 years learning to hold a single particle still, wanting, at the news, to move. And one detail from that laboratory belongs in this story's pocket, because it is the tenderest thing in all of precision physics. In the 1980s, Dehmelt's group held a single positron, one individual particle of antimatter, a character we will meet properly very soon, alone in the trap for approximately 3 months. 3 months of one particle, the same one, circling in its electromagnetic bottle while the team measured it again and again. And somewhere in those months, the particle stopped being an it. The physicists named her Priscilla. In his Nobel lecture, the most formal address a scientist ever gives, Dehmelt referred, without apology, to the well-known positron Priscilla, as if introducing a colleague. Hold on to the irony, because it is the whole coming argument in miniature. The moment a particle is held apart, given a history, tracked as this one and no other, human beings cannot help giving it a name. Individuality for us follows trackability. The question this entire video turns on is whether nature agrees, whether particles have any individuality beyond the tracking, or whether Priscilla was only ever a 3-month-long ripple that someone loved enough to name. And the trap answered one more question along the way, almost as a bonus. How big is an electron? You might imagine it as a tiny ball with a tiny radius. Every attempt to measure that radius has returned the same verdict: too small to see, and smaller than that. From the trap data, Dehmelt extrapolated an upper bound around 10 to the minus 22nd meters. A scale such that if an atom were widened to the size of the Earth, the electron would still be smaller than a marble. Collider experiments, probing directly, certify it point-like down to a billionth of a meter. As far as physics can determine, the electron has no parts, no interior, no size, a pure point of properties. Keep that in mind for later, because things with no parts and no interior are exactly the kind of things that could plausibly be ripples rather than objects. And then the measuring began. An electron is, among other things, a tiny magnet. It has a magnetic strength, and theory makes an exquisitely specific prediction about it, a number called G/2. If the electron were the simplest possible spinning charge, that number would be exactly 1. The corrections beyond 1 come from something we will meet properly later, the restless quantum vacuum the electron drags along with itself everywhere it goes. Measure it, and you get a number. Here it is, the actual number, as of the most recent measurement, published in February of 2023 by a team at Northwestern University. 1.00115965218059. The uncertainty on that value is 13 hundredths of 1 part in a trillion. Let me say that a different way, because the syllables slide past too easily. If that number were a distance of 1 million kilometers, 2.5 times the distance to the Moon, the error bar would be about 1/8 of a millimeter. The width of a grain of salt on a journey to the Moon and back, and most of the way again. It is the most precisely measured property of any elementary particle, and among the most precise measurements human beings have ever made of anything. And here is why it matters to our mystery. That measurement has been repeated on different individual electrons, in different traps, in different decades, by rival teams who would have loved nothing more than to catch each other out. Every electron interrogated this way returns the same number. Not close. The same to every decimal the apparatus can reach. Now push it one step further, because physics did. What about antimatter? You have probably heard the word. Antimatter is real, routinely made, and stored in laboratories. The electron has an antimatter twin called the positron, same mass, same spin, but opposite charge, positive where the electron is negative. In 1987, Dehmelt's group did something almost theatrical in its elegance. They put a single electron in their trap and measured its magnetism, then removed it, put a single positron in the same trap, the same bottle, the same fields, the same conditions, and measured again. A particle of matter and a particle of antimatter, alternately alone in the same few cubic millimeters, asked the same question. The answers matched to 4 parts in a trillion, matter and antimatter agreeing to 12 decimal places. Sit with that for a second, because it sharpens our mystery into something almost unbearable. It is one thing for all electrons to match each other. Maybe, you might think, they all came off the same production line somewhere in the early universe. But the positron is supposed to be the electron's opposite. Why should the opposite of a thing match the thing itself so perfectly, in every property except the sign of its charge? What kind of production line stamps out a particle and its mirror image with the same dye? By the late 1930s, physicists had all these clues in embryo. Identical electrons everywhere, and a strange new mirror particle that had shown up in cosmic rays in 1932, matching the electron in everything but charge. Nobody ordered it. Nobody understood, deeply, why the universe would duplicate its most common particle in reverse. Which brings us to the telephone. It is the spring of 1940. At Princeton, a young graduate student named Richard Feynman, 21 years old, not yet the legend he would become, is at the graduate college when the telephone rings. On the line is his thesis advisor, John-Archibald-Wheeler. Wheeler is one of the great physicists of the century and one of its great wild minds, the man who would later coin the term black hole, who trained a generation of physicists and whose ideas were famous for being either nonsense or prophecy with very little in between. On this day, he cannot wait for a seminar or a paper. He has to say it now, down the wire. We know the conversation word for word because Feynman retold it 25 years later in one of the most famous lectures ever given, and it deserves to be quoted exactly. Wheeler said, "Feynman, I know why all electrons have the same charge and the same mass." Why? Because they are all the same electron. One electron, not 10 to the 80th, one. Here is the picture Wheeler was seeing as he held the phone. Imagine a particle's path through the universe, not just through space, but through time. Physicists call this a world line, a thread that traces where the particle is at every moment of its existence. Now imagine that this one thread does not run politely from past to future the way threads are supposed to. Imagine it is tangled, tied, as Wheeler put it, into a tremendous knot. It weaves forward through time for a while, then turns and weaves backward, then forward again, over and over, a single continuous strand looping through the history of the universe like a scribble filling a page. Now take a knife and cut across the scribble at one instant of time, this instant, say. Your knife crosses the thread not once, but again and again and again, everywhere the tangle happens to pass through the present moment. Each crossing looks, to us, like a separate particle. 1,000 crossings, 1,000 electrons. 10 to the 80th crossings, a universe full of electrons. But there was only ever one thread. And the sameness, the mystery we have spent all this time sharpening, dissolves instantly. Why does every electron have exactly the same charge and mass? For the same reason, every appearance of one actor in a film has the same face. You are not looking at 10 to the 80th things that happen to match. You are looking at one thing, 10 to the 80th times. I want to be honest with you immediately. This idea, in its full glory, is wrong, and we will see exactly why. The evidence against it is devastating and specific, and where that evidence leads is stranger and more satisfying than the idea itself. But before we get there, you need to see the detail inside the phone call that turned out to be pure gold. Because Wheeler's picture contained a second claim, quieter than the first, and that claim did not die. It moved into the foundations of physics, and it is still there tonight. The second claim answers a question you should already be asking. If the thread weaves forward and backward through time, what does a backward stretch look like? When my knife cuts a piece of thread that is traveling from the future toward the past, what do I see? Wheeler's answer: you see a positron. Antimatter, he was saying, is not a separate species of matter at all. A positron is an electron moving backward through time. That sentence sounds like it escaped from a pulp novel, so let us slow it down until it becomes physics instead of poetry, because making that sentence rigorous is precisely what one of the great papers of the 20th century did, and the machinery inside it now sits inside every calculation in particle physics. Run a film of an electron drifting through a magnetic field. The field pushes on the moving charge, and the electron's path bends, say, curling to the left. Now run the film backward. Every velocity reverses, but watch the curl. Played in reverse, the path now bends the other way, exactly the way a positive charge would bend moving forward. A negative charge rewound looks like a positive charge played forward. The mathematics goes deeper than the film trick, but the film trick is the honest heart of it. Reversing a charge's journey through time flips how its charge appears. To understand why anyone would take such an idea seriously enough to rebuild physics around it, you have to go back a dozen years before the phone call, to a piece of mathematics that had been quietly screaming at everyone since 1928. In that year, the English physicist Paul-Dirac wrote down an equation. His goal sounds narrow. Describe the electron in a way that respects both quantum mechanics, the physics of the very small, and Einstein's special relativity, the physics of the very fast. Nobody had managed to make those two frameworks shake hands for the electron. Dirac found the equation that did it, and it is one of the most celebrated lines of mathematics ever written. Spoken aloud, it says, I, gamma mu, partial mu, minus m, acting on psi, equals 0, 5 symbols and a wave function, compact enough to fit on a coffee mug, and physicists put it on their coffee mugs to this day.
Let the symbols soften into a picture, because what that one line accomplishes is astonishing. The psi is the electron itself, described as a wave. The gamma objects are the price of making the wave obey Einstein. Strange, fourfold mathematical gears that had never appeared in physics before Dirac needed them. And when the gears engaged, things nobody had asked for came tumbling out. The equation predicted, unbidden, that the electron must spin. a property physicists had been forced to bolt on by hand before, now emerging from the mathematics like a birthmark. It predicted, before anyone measured it, that the electron should behave like a tiny magnet of a very particular strength, the same magnetic property we met in Dehmelt's trap, predicted here at its simplest value, decades before the trap existed. The prediction landed almost exactly on the measured value. Physicists knew immediately they were holding something true, almost exactly, and the almost became one of the greatest stories in science, worth 30 seconds of our time because it explains why anyone bothers measuring a magnet to 12 decimal places. Dirac's equation says the electron's magnetic number should be exactly 2 in the natural units physicists use. Measure carefully and you find 2.002 and change, a whisper more. That whisper is not error. It is the quantum vacuum itself. The electron, it turns out, is never truly alone, but constantly surrounded by a fizz of particles flickering in and out of existence, and the fizz drags on its magnetism ever so slightly. In 1948, Julian-Schwinger calculated the first sliver of that drag from pure theory, and the answer, the fine structure constant divided by 2 pi, in words, a small known number divided by roughly 6, matched the measurement. His formula is carved on his gravestone. Every further decimal in Dehmelt's and Northwestern's measurements is a deeper interrogation of that vacuum fizz, and the theory has answered correctly at every decimal so far. When physicists say quantum electrodynamics is the most precisely tested theory in human history, this number, the whisper above 2, is the test they mean. But the equation came with a shadow. Alongside its sensible solutions, electrons with positive energy doing electron things, the mathematics stubbornly produced a second family of solutions with negative energy. Not small energy, negative, less than nothing, and you could not throw them away. Delete them and the mathematics fell apart. Worse, quantum mechanics said an ordinary electron should be able to tumble down into these negative states, releasing energy as it fell, then keep tumbling, forever, down a bottomless staircase. If the negative solutions were real, no atom in the universe should be stable. Yet there the atoms were, insolently existing. Dirac's first rescue attempt in 1930 was gloriously desperate. Suppose, he said, the bottomless staircase is already full. Suppose all of empty space, the vacuum itself, is packed solid with an infinite invisible sea of negative energy electrons, filling every level so that ordinary electrons have nowhere to fall. What we call nothing would actually be infinitely full. And if you knocked one electron out of the sea, gave it enough energy to jump up into the ordinary world, it would leave behind a hole. That hole, a missing negative charge in an infinite negative background, would look to us like a positive particle. 2 years later, in 1932, Carl Anderson at Caltech, photographing the tracks of cosmic rays, found a particle curving the wrong way. Electron mass, positive charge. The positron. The hole in Dirac's sea, apparently, was real. Prediction, then discovery. One of the great 1-2 punches in the history of physics. And before we return to the sea, notice where that wrong-way particle ended up. Because it did not stay in the philosophy books or the cloud chambers, it is in your local hospital, saving lives on an ordinary Tuesday. A PET scan, positron emission tomography, works by injecting a patient with sugar tagged with a mildly radioactive atom, usually fluorine-18. As that atom decays, it does something Dirac's equation demanded and Anderson photographed. It emits a positron. Antimatter, manufactured inside a human body, on purpose, by a machine down the corridor from the gift shop. The positron travels about 1 millimeter through tissue before it meets one of the body's own electrons, and the two annihilate,
matter and antimatter cancelling, releasing two flashes of gamma light that fly apart in exactly opposite directions. The scanner is a ring of detectors waiting for those paired flashes. Catch both, draw a line between them, and the annihilation happens somewhere on that line. Millions of lines later, the machine has drawn a map of where the body is burning sugar fastest, which is how oncologists find tumors, because tumors feed greedily. Sit with the chain of custody on that idea, an equation with embarrassing solutions, a desperate infinite C, a student's phone call about time running backward, and now a device that finds cancers early enough to cut them out. Every PET image ever taken is a photograph of electron-positron annihilation. The meeting of a forward thread and a backward one, in Feynman's picture the same thread turning around, put to work. When people ask what abstract physics is for, this is the answer with the shortest path from chalkboard to heartbeat. And yet almost nobody, deep down, loved the sea. An infinite ocean of invisible particles, everywhere, forever, with infinite charge and infinite energy that we simply agree not to notice. It gave the right answers while feeling like a magician's misdirection. Feynman himself said the whole theory had caused him, as a student, more logical difficulty than almost anything else. The sea worked. Nobody could say why the universe should be built that way. That is the itch Wheeler's phone call was scratching. And it is the itch that Feynman, and, we will see, another man before him, working alone in Switzerland, finally cured by taking the backward-in-time picture seriously and doing what Wheeler never did, the mathematics. Feynman's verdict on the phone call, delivered decades later, splits it perfectly down the middle. The grand claim, one electron for the whole universe, he did not believe for a moment, and he told Wheeler so on the spot, with a young student's directness. We will come to his exact objection soon, because it is the first crack in the beautiful idea, and the crack runs all the way down. But the smaller claim lodged in him and never left. In his Nobel lecture, Feynman said it plainly. The idea that positrons could simply be represented as electrons going from the future to the past, that I stole.
What does it mean to steal an idea like that and make it physics? It means writing down equations in which the statement stops being a metaphor and starts being machinery. In 1949, Feynman published a paper titled The Theory of Positrons, and in it, the negative energy solutions of Dirac's equation, the bottomless staircase, the infinite sea, all of that anguish, are reinterpreted in one clean stroke. The troublesome solutions, Feynman showed, are not electrons falling into an abyss. They are waves traveling away from the interaction backward in time, and read in the ordinary direction, along with the rest of us, each one is a positron moving forward. The sea evaporates. Nothing is infinitely full. There is no bottomless staircase. There are only electrons threading through space-time in both directions, and we, who insist on reading time left to right, see the backward stretches as antimatter. In the appendix of that paper, Feynman proved the new picture gives exactly the same experimental predictions as the old machinery. This was not a rival theory. It was the same theory with the fog burned off. And the tool he built to do the bookkeeping, little diagrams of particle paths with antiparticles drawn as arrows pointing backward against the flow of time, became the universal language of particle physics. Every working particle physicist on Earth today draws Feynman diagrams the way musicians read notation, and in every one of those diagrams, on every whiteboard in every physics department in the world, antimatter is still drawn exactly as Wheeler blurted it down the phone, as matter running the other way through time. It is worth pausing on how close that mathematics came to never being finished, because in 1947 the whole framework was drowning, and the story of its rescue is one of the best 2 years physics ever had. The problem was infinity. Whenever anyone tried to calculate the vacuum's whisper, the electron interacting with its own field, the effect behind that 11 decimal magnetic number we met earlier,
The equations returned not a small correction, but an infinite one. Every calculation, pushed honestly, exploded. Some of the greatest physicists alive quietly suspected the whole theory was rotten at the foundation. Then, in June of 1947, 24 physicists gathered at a small inn on Shelter Island, off the tip of Long Island, and heard experimental news that turned despair into a deadline. Willis-Lamb, a master experimenter, reported that two energy levels of hydrogen, which the existing theory said must be exactly equal, were not equal. They differed by a tiny, stubborn, unmistakable amount. The vacuum's whisper was not optional anymore, and not infinite either. There it was, measured, small, and finite. The theory that could not compute a finite number had just been handed the finite number in public.
Hans Bethe famously could not wait. On the train home from the conference, he attacked the calculation with a deliberately rough shortcut, subtracting one infinity from another and trusting the difference. And before the trip was over, he had a number close to Lamb's measurement. The message of that train ride was electric. The infinities were not a disease of nature, they were a disease of bookkeeping, and they could be tamed. Over the following 2 years, 3 men, working separately in styles so different they could barely read each other, built the tame version properly. Julian-Schwinger, in a formalism of legendary density, derived the first correction to the electron's magnetism, the number that started the 11-decimal hunt. Sin-itiro-Tomonaga, astonishingly, had already found the same structure years earlier in wartime Japan, cut off from every Western journal, publishing into a void that only later learned to listen. And Feynman got there with his diagrams, the backward-pointing arrows borne on Wheeler's telephone, which turned month-long calculations into afternoon ones. In 1965, the three shared the Nobel Prize for it. The framework they saved, quantum electrodynamics, went on to become the most precisely verified theory in the history of science. And the machinery inside it that makes the infinities cancel leans, at every step, on antimatter behaving as matter reversed. Pull the backward thread out of the mathematics and the rescue collapses. So the second half of the phone call is not a curiosity. It is load-bearing. Modern physics does not merely tolerate the time-reversed picture of antimatter, it is built on it. And built on it is not a figure of speech. It is checked, daily, in machines the size of towns. Here is how you test whether antimatter really is matter reversed. The mathematics makes a startling claim called crossing-symmetry. The equations describing two electrons bouncing off each other, and the equations describing an electron bouncing off a positron are the same equations. One is the other with a particle's direction through time flipped. Two apparently different experiments, one calculation. If Feynman's picture were decoration, that identity would fail somewhere in the decimals. So physicists made both collisions workhorses. Electron-positron scattering is so well predicted that the great colliders used it as their ruler. The process was computed so precisely that counting those events is how the machines calibrated everything else they measured, trusted at the level of 0.1% and beyond. At the LEP collider at CERN, hundreds of millions of collisions agreed with calculations whose entire logic assumes the positron is an electron on a reversed world line. The backward-in-time picture is not philosophy. It is calibration-grade engineering fact. And the deepest version of the test is the one we already met in Dehmelt's bottle, the mirror itself. If antimatter is matter time reversed, particle and antiparticle must match exactly. Same mass, same magnetism, opposite charge. The electron and positron match to 4 parts in a trillion. At CERN, a collaboration called BASE performed the same interrogation on the proton and antiproton, comparing their charge to mass ratios, identical to 16 parts in a trillion. Every such test, on every particle, at every precision ever reached,
has come back the same way. The mirror is perfect as far as human instruments can see, precisely what the reversed thread mathematics demands, and it checks out to extraordinary precision every day someone looks.
The most theatrical version of the mirror test deserves its minute because it sounds like science fiction and is running right now in a building you could visit. At CERN, physicists do not just make positrons, they build entire antiatoms. Slow an antiproton until it is barely crawling, introduce a positron, and the two bind exactly the way a proton and electron do. Antihydrogen, a complete atom of antimatter. The positron orbiting its antinucleus in the same quantum ladder of energy levels as ordinary hydrogen. The hard part is not making it, it is keeping it, since an antiatom that grazes any wall of any container vanishes in a flash of gamma light. So the alpha collaboration holds its antiatoms in a bottle made of nothing, a sculpted magnetic field, gripping them by their faint magnetism, untouched by matter, sometimes for hours. And then comes the exam. Shine a laser on trapped antihydrogen and ask it the most personal question you can ask an atom. What are your energy levels? Hydrogen's answer, a particular transition frequency, is one of the most precisely measured numbers in all of science. Antihydrogen's answer, announced in 2018, identical to 2 parts in a trillion. The anti-atom sings the same note. Even gravity has now been asked. Antimatter atoms, dropped in vacuum, fall down, not up, just as relativity insisted they must. Understand what this means for our story. The identicality that launched this whole journey does not merely hold across all electrons everywhere. It reaches across the mirror, binding each particle to its time-reversed twin with the same infinite decimal exactness. Whatever stamps the copies, it stamps both sides of the mirror from a single die. And note, while the die is on the table, that the stamping is not an electron privilege. The electron has a heavier sibling called the muon, 200 times the mass, identical charge, identical spin, living a fleeting 2/millionths of a second before decaying. And every muon ever measured is exactly like every other muon, to the finest precision reached. Same for every photon, every quark of a given type, every neutrino of a given kind. Nature does not run one strange monopoly in the electron department and handcraft individuals everywhere else. Perfect duplication is the universal manufacturing standard of reality, enforced in every particle family without a single recorded exception. Whatever answer explains the electrons had better be the kind of answer that repeats. One explanation per family, the same trick each time. Keep that requirement in mind when the candidates start auditioning. It will quietly eliminate half of them. A story that only works for one particle family is not an explanation. It is a coincidence wearing an explanation's coat. Which leaves the first half. The grand half. One electron, one thread, one tremendous knot. The single most economical explanation for perfect identicality ever proposed. It explains, in one sentence, the deepest sameness in nature. And it is wrong. What kills it is not a philosophical objection or a failure of taste. It is arithmetic. 3 separate pieces of arithmetic, each fatal on its own. And the very first one was spotted in the first 60 seconds, by a 21-year-old graduate student holding the phone. Before we get to the count that breaks the beautiful idea, we should let the 2 men in this story become people, because one of them you know, and the other walked away into one of the quiet tragedies of modern physics. If you are enjoying following this thread the way it deserves, slowly, all the way down. A quiet tap on subscribe helps more explorations like this one find the people who stay up at night wondering about them. Wheeler first. John-Archibald-Wheeler is one of the strangest and most consequential figures in 20th century physics, precisely because he refused to stay respectable. He worked with Niels Bohr on the physics of nuclear fission in 1939, taught at Princeton for decades, and supervised the doctorates of an astonishing lineage of physicists, Feynman among them. But his signature was the outrageous idea, floated with complete sincerity, defended with charm,
and abandoned without embarrassment when it failed. Every electron in the universe is one electron. The laws of physics themselves may be mutable. He treated ideas the way a prospector treats streams: pan everything, keep the glints, discard the gravel without mourning it. Most of the glints were pyrite. A few were gold, and one of the gold ones has a name he coined that you already know: the black hole. That is the man who could not wait to dial his student in the spring of 1940. Decades later, in his memoir, Wheeler was cheerfully candid that even he had not taken the one-electron universe fully seriously. It was a flare fired into the dark to see what it lit up. Feynman you have met, or think you have. In 1940, he was not yet the bongo-playing Nobel laureate of the anecdotes. He was a graduate student with a reputation for seeing through to the bones of a problem faster than anyone around him. What matters for our story is the shape of his genius. He had no reverence whatsoever for how an idea arrived: phone call, dream, joke, and total reverence for whether it survived calculation. An idea from the most eminent man in the department got 60 seconds of hospitality and then had to face the numbers like everybody else. Keep that in mind for what comes next, because the first fatal number arrived within that first minute. And there is a third man who was not on the phone, and whose absence from this story's fame is its quiet injustice. His name was Ernst-Stueckelberg, a Swiss physicist working in Geneva. In 1941, before Feynman published anything on the subject, Stueckelberg worked out, with real mathematical care, the picture of a single particle's world line advancing and retreating through time, with the backward stretches behaving as antiparticles, pair creation and annihilation appearing naturally as the turning points of one continuous path. He published in French, in a Swiss journal that almost nobody outside Switzerland read, in the middle of a world war. He struggled with bipolar illness through much of his life. Recognition largely passed him by. Years later, after Feynman delivered a lecture in Geneva, Feynman watched Stueckelberg leaving quietly with his dog and said to those near him, "He did the work and walks alone toward the sunset, and here I am, covered in all the glory, which rightfully should be his." Physics now speaks of the Feynman-Stueckelberg interpretation, an act of posthumous justice in a hyphen. Hold Stueckelberg in your mind, the man who did it first, alone, in the dark. We will meet his sunset again at the end.
It is worth one more minute on Wheeler himself before the arithmetic, because the phone call was not an aberration, it was his method, and his method changed physics twice more in ways that echo through this channel's stories. Decades after the electron call, Wheeler became captivated by another impossible-sounding question: whether information, not matter, might be the true foundation of reality. A program he compressed into 3 words: it from bit. He spent his later years asking students questions like, why does the universe require observers, and what is an observation, really? Most of it remains beyond testability, exactly like the one-electron universe. But scattered through the untestable flares were ideas that landed. He pushed a skeptical physics community to take black holes seriously enough that he ended up naming them. He co-invented the framework by which quantum mechanics gets applied to the universe as a whole. And his habit of asking outrageous questions in complete sincerity trained the generation, Feynman first among them, that built modern physics. His memoir's honesty about the 1940 call is the model of how science should hold its wild ideas. He admitted the one-electron universe was never fully serious, and defended to the end the practice of saying such things out loud. The flares that fail cost nothing but embarrassment, he understood. The ones that land pay for a century of misses. There is also a human asymmetry between the 2 men on the phone worth noticing, because it decided what happened to the idea. Wheeler generated, Feynman filtered. Wheeler's gift was to produce candidate truths faster than anyone could check them.
Feynman's was a filter of almost frightening efficiency, an inability to believe his own or anyone's beautiful idea 1 minute longer than the evidence allowed. Neither gift works alone. A field of pure Wheelers drowns in its own speculation. A field of pure Feynmans starves for want of anything audacious to test. The one-electron universe is the perfect fossil of their collaboration, generated in one mind, filtered in another, the gold separated from the gravel inside a single phone call. And the gold, the backward-in-time positron, carried off by the student with the filter, who then spent 9 years turning it into mathematics that could face experiment. Now, the arithmetic that kills the beautiful idea. Go back to Wheeler's knot, one thread weaving forward and backward through time. Cut it with the knife of now. Count the crossings. Here is the unavoidable bookkeeping fact about any single continuous thread. It must turn around between a forward stretch and a backward stretch. Every time it turns, one forward crossing and one backward crossing meet. Follow the whole tangle from end to end and the accounting is strict. The number of forward crossings and the number of backward crossings can differ by at most 1, the two loose ends of the thread. One thread means the universe's electrons and positrons must show up in almost exactly equal numbers. Half the crossings are electrons, half are positrons, give or take 1. Feynman saw this instantly and said so into the phone. But Professor, there aren't as many positrons as electrons. And there aren't, not remotely. Look around. Every atom in your body, in the Earth, in the Sun, in every star we can see, uses electrons. And none of them uses positrons. Positrons are exotic. They appear in cosmic ray strikes and radioactive decays and hospital PET scanners, and the instant one meets an electron, the two annihilate in a flash of light. Matter, electron-flavored matter, owns the universe. The backward crossings are missing, not a few of them, essentially all of them. Wheeler's reply, quoted by Feynman with obvious affection, was magnificent hand-waving. Well, maybe they're hidden in the protons or something. Maybe the missing backward stretches are tucked away inside other particles where we cannot count them. It was a shrug, and Wheeler knew it. Nothing was hiding in the protons. The count stands, and the count is the first fatal wound. One thread demands a matched population, and the universe flagrantly refuses to provide it. But it is worth pausing on how deep the refusal goes, because when physicists chase down where the imbalance comes from, they found a number that has become one of the most haunting in all of science. And it is a number about you. Run the film of the universe backward, toward the beginning, hotter, denser, brighter. In the ferocious energy of the first moments, matter and antimatter were being created constantly, always in pairs. Every electron born with a positron, particle and antiparticle, forward and backward, in perfect balance, exactly as the deep symmetry of the equations demands. Run the film forward again and the universe cools, and the pairs meet and annihilate, matter and antimatter erasing each other back into light, pair by pair, everywhere, an almost perfect cancellation of everything. Almost. For roughly every billion matter-antimatter pairs that annihilated into light, one extra particle of matter, just one, with no partner, survived. The measured imbalance is about 1 part in a billion. Everything you have ever seen, touched, loved, or been is built entirely out of those unpartnered survivors. The stars are made of the leftover. The Earth is the leftover. You are the leftover, the residue of a cancellation that came within 1 part in a billion of being total. Before you accept that accounting, you should ask the skeptic's question, because astronomers asked it for decades. How do we know the missing antimatter is actually missing? Maybe the universe is even-handed after all, and the positrons simply live somewhere else. Whole galaxies of antimatter, with anti-stars fusing antihydrogen, shining with light that would look absolutely identical to ordinary starlight, since the photon is its own antiparticle and carries no allegiance. You cannot tell an antimatter galaxy from a matter galaxy by looking at it. but you can catch it touching its neighbors. Galaxies are not islands. They swim in tenuous gas, and gas from one bleeds into the space around the next. If any region of antimatter bordered a region of matter, the contact zone would be a permanent battlefront. Every meeting of atom and anti-atom flaring into gamma rays of a precise, unmistakable energy, a boundary drawn across the sky in annihilation light. Gamma-ray telescopes have mapped the sky for half a century. The glowing borders are not there. Not between galaxies, not between clusters, not anywhere out to the edge of the observable universe. And the direct searches agree. Instruments have sifted cosmic rays for a single heavy anti-nucleus. One anti-helium arriving from some distant anti-star would rewrite the field overnight, and no confirmed candidate has survived scrutiny. A detector the size of a room, the Alpha Magnetic Spectrometer, has ridden on the International Space Station for over a decade doing exactly this hunt. The universe we can see is matter, all the way out. The annihilation was real, the leftover is everything, and the imbalance is not hiding, it is genuinely unexplained.
Where the tiny imbalance itself came from is one of the great open problems in physics, and the story of the search is worth telling properly because it shows how seriously nature guards this particular secret. In 1967, the Soviet physicist Andrei Sakharov, who led two utterly different lives, first as father of his country's hydrogen bomb, later as its most famous dissident and a Nobel Peace Laureate, wrote down in a 3-page paper the complete list of conditions any universe must satisfy to end up with more matter than antimatter. One of the three is the crucial one for us. The laws of physics themselves must treat matter and antimatter at least slightly differently. Perfect even-handedness, and every pair annihilates. Nothing survives. No stars, no chemistry, no one to wonder about it. So physicists went hunting for the unfairness, and they found it. At two great experiments, one at Stanford called Barbar, one in Japan called Bell, physicists produced particles called B mesons by the hundreds of millions, together with their antimatter twins, and timed how each decayed. In 2001, both teams announced the verdict. The twins do not behave identically. Matter and antimatter versions decay at measurably different rates. The bias is real, quantified, confirmed, and it earned the physicists who predicted its mechanism a Nobel Prize. The laws of nature really do play favorites. For a moment, it looked as if the mystery of our survival was solved. Then came the arithmetic and the humbling. Take the measured unfairness, feed it into the physics of the early universe, and ask how much matter survives the Great Annihilation. The answer falls short of what exists, not by a little, but by many orders of magnitude. The favoritism is real, but far too feeble. By its accounting, the universe should be an empty hall of light with barely a dust grain of matter in it. Something else, still undiscovered, tipped the scales. Some deeper asymmetry that our accelerators have not yet reached. Nobody knows what it is. That mystery stays open tonight, and it is one of the handful of questions on which the next revolution in physics may hinge. But notice what this whole detour means for Wheeler's thread, because it is worse for the thread than a simple imbalance would be. The imbalance is not decoration on the universe. It is the reason there is a universe worth the name. And the thread cannot have it. A single continuous world line is the one architecture in which matter and antimatter crossings are forced, by pure topology, into balance. The universe is not a balanced tangle. It is almost pure forward thread, the backward stretches annihilated in the first moments, the survivors outnumbering their vanished partners 1,000,000,000 at birth. One continuous thread cannot be cut into a trillion forward crossings and essentially 0 backward ones. The geometry does not exist, and what forbids it is the very fact that anything exists at all. I know that was a dense stretch of road, so pause and feel where you are standing. That warmth when you rest your palm against your own arm. Every particle of it is a 1 in a billion survivor of the universe's opening act. The idea we are testing says all those survivors are one traveler. The count just told us that cannot be.
2 more blows are coming, and then something better than the thing being broken.
The second blow. Electrons are not permanent. Wheeler's picture needs the thread to be continuous, a world line you can trace without lifting the pen. But nature lifts the pen. In a common form of radioactive decay, a neutron inside a nucleus transforms, and an electron is created in the act, not summoned from somewhere, not already existing and merely arriving, created on the spot where there was none. Other processes destroy electrons outright, their identity passing into different particles entirely, neutrinos which are not electrons at all, not even backward ones. The thread does not just weave, it begins in some places and ends in others, spliced into the wider web of particle transformations. A single continuous strand cannot begin and end thousands of times a second in every gram of radioactive rock on Earth. The third blow is the quietest and, for physicists, the most decisive. If every electron is literally the same object at different points of its journey, then 2 electrons measured in 2 laboratories are self-correlations of one traveler, and building the observed quantum correlations that way, for particles measured at the same moment on opposite sides of a continent, cannot be arranged without the influence outrunning light. Quantum mechanics produces those correlations naturally for 2 genuinely distinct particles sharing one quantum state. It cannot produce them as one particle's diary entries without breaking causality itself. Entangled pairs, now bread and butter laboratory physics, are the third strike. So the beautiful idea is dead, 3 times over. And now you should feel the vacuum it leaves behind, because the original mystery is still sitting on the table, sharper than ever. The one-electron universe died, but it was the only explanation in the room for the fact we started with. 10 to the 80th particles, identical to 12 decimal places, including their own antimatter mirror. If they are not all one particle, then what in the world are they? Here is where the story turns, and I will be honest, the true answer, the one physics settled on, is stranger than Wheeler's. It just hides its strangeness better. The answer is called quantum field theory, and the cleanest way in is to notice what kind of question "why are they identical?" is. When 2 things match perfectly, the same conclusion is that they are not independent, that some single underlying thing accounts for both. Wheeler made the single thing a particle, threading through time. Quantum field theory makes the single thing something larger, a field filling the universe. Do not let the words slide past. The claim is radical. According to quantum field theory, the framework underlying all of particle physics, the most precisely confirmed scientific theory ever constructed, the basic furniture of reality is not particles at all. It is fields, continuous, invisible somethings that exist everywhere at once, at every point of space, at every moment. There is an electron field, one single field, present in the room with you now, present in the space between galaxies, present inside your bones. One seamless entity spanning the entire universe. What we call an electron is not a little ball of stuff. It is a ripple in that field. A localized hum of excitation, like a wave traveling on an infinite ocean. Because field is a word physicists use casually and everyone else finds slippery, take a minute to actually build the picture from something you already trust. Start with temperature. Every point in your room right now has a temperature. Near the window, slightly cooler, near your body, slightly warmer. That assignment of a number to every point of space is a field. Nothing exotic yet, just a map with infinitely fine resolution. Now make the map physical instead of descriptive. Picture the surface of a pond at dawn, perfectly still. At every point, a height, all of them level. Disturb one spot and the heights ripple. And here is the detail that carries all the weight. Nothing travels across the pond. No object journeys from the splash to the far shore. Each parcel of water only bobs in place, handing its motion to the neighboring parcel, which hands it on. What travels is the pattern.
The wave is a shape passing through a medium whose parts barely move at all. Now perform the final promotion, the one quantum field theory demands. Delete the water. Keep the mathematics of the rippling, the field of values at every point, the handing on of disturbance from neighbor to neighbor, but let it need no substance underneath, because it is the substance. That is the electron field, not a material spread through space, but the layer of reality one level beneath material, out of which material is made. It has a value at every point in this room, in your bones, between the galaxies. Where it hums in the right localized way, instruments register what we call an electron. Where it lies in its restless minimum, we call it vacuum, though, as we saw at Northwestern, even the vacuum hums too faintly quiet to be nothing. If some part of you protests that this is too strange to be the actual world, that ripples need something to ripple in, know that this protest has a distinguished history. Physicists of the 19th century insisted light waves needed a medium too, named it the luminiferous ether, and spent decades hunting for it. And the hunt itself, in one of the most famous null results ever recorded, proved the medium did not exist. The waves are real, the water was never there. Physics has been slowly making peace with that sentence for a century and a half, and the electron field is its fullest expression. When you tap the table and it resists, that resistance is field arithmetic. There was never anything else for it to be. And before we cash in the answer, you deserve to see what perfect identicality is for, because it is not a curiosity. It is the reason you exist, through one of the most consequential rules in all of physics. In 1925, Wolfgang Pauli noticed that atoms only make sense if electrons obey a strange prohibition. No two electrons in an atom may occupy exactly the same quantum state. It is called the exclusion principle, and here is the crucial point. It only applies, and can only apply, to particles that are perfectly identical. The prohibition is enforced by the swap mathematics we will meet in a moment. Exchange two truly identical electrons, and the mathematics flips a sign, and that sign flip makes any state where two of them sit in identical circumstances cancel itself out of existence. Two merely similar particles could pile into the same state without objection. Perfectly identical ones cannot. Now follow the consequences up the ladder, because they go all the way to your hands. Because electrons exclude each other, they cannot all collapse into an atom's lowest orbit. They are forced to stack, shell upon shell, each new electron obliged to take the next seat up. Because they stack in shells, different elements, different electron counts, end their stacks differently, and the outermost, unfinished shell is what an atom offers to the world. Chemistry is the negotiation between unfinished outer shells. Carbon's 4-seat vacancy makes it the universal connector on which every living molecule is strung. The rigidity of the table under your hand is electron exclusion refusing compression. The periodic table, chemistry, biochemistry, the solidity of matter, you, the whole tower stands on the exclusion principle, and the exclusion principle stands on electrons being not similar, but strictly mathematically identical. If electrons differed by a part in 1,000 or a part in 1,000,000,000, the prohibition would evaporate, atoms would collapse into featureless droplets, and no structure in the universe would exist to wonder why. Feel how that raises the stakes of our mystery. The sameness on the table is not trivia. It is load-bearing for reality. Whatever explains it, explains why there is chemistry at all. And here is what should genuinely unsettle you. Nature was leaving confessions about this long before anyone could read them. In the 1870s, half a century before quantum mechanics, before anyone had even proven atoms exist, the American physicist Josiah Willard Gibbs stumbled into a paradox while working out the theory of mixing gases. Open a valve between a chamber of one gas and a chamber of a different gas, and disorder increases by a definite, calculable amount as they mingle. That is standard thermodynamics, the same bookkeeping that runs steam engines. But run the identical calculation for two chambers of the same gas, and the mathematics of the era face-planted. Treat the molecules as tiny individuals, each with its own identity, and mixing same with same should also raise the disorder. Those particular molecules from the left are now spread everywhere, after all. Yet measurably, nothing whatsoever happens. Open the valve between identical gases and every thermometer, every pressure gauge, every engine you could attach agrees, no change. The only way to make the arithmetic match the instruments is to declare something scandalous for 19th century physics: that swapping two molecules of the same gas does not produce a new arrangement of the world. Not an arrangement too similar to notice, the same arrangement counted once. Gibbs wrote down the corrected counting rule without being able to say why nature enforced it. The reason arrived 50 years later. The molecules' electrons and protons are field ripples with no individual identity to track. A 19th century engineer's puzzle about gas valves was quantum field theory clearing its throat. There is a cosmic scale version of this confession too, and it is one of the quietly astonishing facts of astronomy. When astronomers point telescopes at the most distant quasars, light that left its source over 12 billion years ago, from regions that have never exchanged so much as a photon with our neighborhood, they read that light by its spectral lines, the barcode printed by electrons hopping between energy levels in atoms. And the barcode is our barcode. Hydrogen at the edge of the observable universe, in the universe's first 2 billion years, prints the same pattern as hydrogen in this room, because its electrons carry the same mass, the same charge, the same magnetism as the ones in your hand. Astronomers have hunted hard for even a drift in the fine structure constant across those billions of years. It would be a Nobel Prize waiting in the data, and the answer keeps coming back. No confirmed variation, anywhere, ever. Think about what is being claimed. Every electron we have ever interrogated, in Dehmelt's bottle, in a hospital scanner, in starlight 12 billion years old, is not approximately standard. It is perfectly standard across all of space and all of cosmic time. That is the fact demanding explanation. Whatever answer you give had better cover the entire universe and its entire history, because the sameness demonstrably does. Now watch the mystery of identicality simply evaporate. Why is every wave on the same ocean made of the same water? The question embarrasses itself in the asking. Ripples of one medium are made of that medium, necessarily, automatically, without any coordination required. The physicist Frank Wilczek, a Nobel laureate, states it exactly. Two electrons anywhere in the universe, whatever their origin or history, are observed to have exactly the same properties, and we understand this as a consequence of the fact that both are excitations of the same underlying stuff, the electron field. Every electron in your hand, in the table, in the farthest galaxy. The same one field, humming in 10 to the 80th places at once. Feel what just happened to Wheeler's idea. It was not discarded, it was promoted. He said, "The reason electrons are identical is that they are all one thing." Physics answered, "Correct, but the one thing is not a particle tracing a tangled path through time. The one thing is the field, and it does not need to travel from place to place to be everywhere, because it already is everywhere." Wheeler's intuition, one entity, many appearances, survives at the very foundation of physics. Only the geometry changed. Not one thread, weaving. One ocean, waving. And the positrons? Quantum field theory keeps Feynman's stolen treasure whole. The electron field's equations contain both ripple families,
and antimatter remains, in every calculation, mathematically interchangeable with matter running backward in time. That is still how it is computed, drawn, and taught. The field picture even repays an old debt. Where Wheeler's thread demanded equal populations and choked on the imbalance, the field simply hums however the universe's history requires. More electron ripples than positron ripples, pair creation here, an unpartnered survivor there. Everything the thread could not accommodate, the ocean absorbs without strain. Before the jewel at the center of this, one honest question deserves airtime, because you may already be asking it. Is the field real? Or is it just mathematics, a bookkeeping device physicists find convenient? It is a fair challenge, and physics has an unusually direct answer. The field shows its reality precisely where there are no particles at all. Take a region of perfect vacuum. No electrons, no ripples, nothing. The electron field is still there, and quantum mechanics forbids it from being perfectly still, the way it forbids anything from being perfectly still. The field's restless minimum, that vacuum fizz we met earlier, is not hypothetical. It is exactly what drags the electron's magnetism above Dirac's clean value of 2, producing the whisper that Schwinger calculated and Northwestern measured to 12 decimals. The agreement between that measurement and that calculation is the empty field itself, weighed. An ocean you can weigh even when it is calm has earned the word real. The same move settles an old philosophical account. Leibniz declared no two things in nature perfectly alike, and for 3 centuries every leaf and snowflake obeyed him. Electrons disobey, and the field explains why without breaking the principle's intent. Leibniz was right about things. Genuine objects, with their own histories and their own matter, always differ. His principle fails for electrons because electrons were never things. They are repetitions, the same entity's behavior performed in many places. The exception to the oldest rule about objects turns out to be the fingerprint distinguishing objects from appearances. Wherever you find perfect identicality, you are not looking at many things. You are looking at one thing many times. Hold that sentence. It is about to be asked to carry more weight than physics. There is a mathematical jewel at the center of this, and it deserves one careful minute, buffered gently, because it turns identical from an observation into a theorem. In quantum mechanics, the deepest test of whether two things are truly identical is what happens when you swap them. Take a system containing 2 electrons, exchange them, and ask what changed. If the two were distinguishable in any way at all, any difference, however small, the swap would produce a physically different situation. What the mathematics of the electron field enforces is stark. Swapping 2 electrons changes nothing observable at all. The equations do not merely permit their indistinguishability. They refuse to contain any means of telling them apart. The theory has no slot where an individual identity could be written. Here is the buffer, the picture to carry. Think of 2 ripples crossing on a pond. While they overlap, ask which ripple is which as they emerge. The question has no answer. Not because you lack the eyesight, but because ripples are not the kind of thing that carries a name tag. They are shapes in one shared water. Electrons are shapes in one shared field, and asking which is asking the water to remember something it never recorded. And this refusal has a visible fingerprint, a place where you can watch indistinguishability push particles around in the laboratory. Fire 2 electrons at each other and detect where they scatter. For distinguishable particles, there are 2 distinct stories. Mine deflected left, or yours did, and you add the chances of each story. But for identical particles, the 2 stories are indistinguishable even in principle, and quantum mechanics then demands something eerie. The stories interfere, like overlapping waves, cancelling and reinforcing.
For electrons, the mathematics of that interference forbids them outright from scattering at exactly 90 degrees to each other. Not discourages, forbids. Detectors at the right angle sit silent forever, purely because the two particles are too identical for the universe to tell their stories apart. Sameness in quantum mechanics is not bookkeeping. It reaches into space and steers matter. And the field picture wins a final, quietly decisive argument over the particle picture. One articulated by Freeman-Dyson, the physicist who proved that the various formulations of quantum electrodynamics were secretly the same theory. Dyson granted the backward-in-time move its full due. A positron, he wrote, can be regarded as precisely equivalent to an electron propagating backward. But he put his finger on the asymmetry between the pictures. In a particle-based view, the fact that there are many electrons, all indistinguishable, has to be inserted by hand as a special assumption bolted onto the theory. The field derives it. Start from one field, and indistinguishability is not an axiom but a consequence. You could not build distinguishable electrons out of one field if you tried. When one framework must assume the central mystery and a rival framework proves it, the argument is over. That is what physicists mean when they say the field is deeper than the particles. Honesty requires the ledger's other column too, so here it is. The field picture has one soft spot, and it is philosophical rather than experimental. The word excitation is crisp for a ripple that starts and stops, but an electron that lives forever, never created and never destroyed, sits oddly under a word that suggests a temporary disturbance. What exactly is waving, and in what sense does a permanent wave differ from a thing? Philosophers of physics genuinely argue about this, and the argument is worth having. But notice its shape. It is a dispute about which words carve the mathematics most truthfully, not about any measurement. Every experiment ever performed agrees with the field's equations. The soft spot is in our language, not in nature's answers. That is the resolution the evidence supports. Not 10 to the 80th separate things that happen to match. Not one thread heroically weaving. One field, and every electron that has ever existed, in every atom of every star and every cell of every living thing, a ripple in it. Let the everyday version land before we walk to the edge, because it belongs to you and not to any laboratory. Press your thumb against your wrist and find the pulse. The blood moving under your thumb is iron and oxygen and water, and stitched through every atom of it are electrons. Ripples, we now know, of a field that also ripples in the wood of your table, in the salt of the oceans, in the light-collecting cells of your eyes. The same field ripples in a star so far away its light left before your grandparents were born. Nothing in you is made of private matter. At the particle level, there is no such thing as your electrons. There are places where the universal field is, briefly and magnificently, arranged into the pattern that is you. You are not a collection of tiny possessions. You are a performance, the one field, playing a figure it has never played before and will never play again, in an auditorium where every other performance is being played by the same performer. There is one more everyday fact that belongs beside the pulse, and it quietly finishes the argument the field started. The matter performing you is not even on loan long-term, it is passing through. The atoms of your body turn over relentlessly, the lining of your stomach in days, your skin in weeks, your red blood cells in about 4 months, even your skeleton remodeling itself across a decade. Year by year, the overwhelming majority of the particular atoms in you are exchanged for others from food, water, and air, and their electrons, perfectly identical, remember, so nature keeps no receipts, disperse into soil and sea and other living bodies without any possible forwarding address. The you of 10 years ago and the you of tonight share almost no matter worth mentioning, and yet no one, not you, not anyone who loves you, considers that a death. Why not? Because what you are was never the inventory. It is the pattern the inventory briefly performs, held stable while every performer in the orchestra is replaced mid-note. You already believe, in other words, casually in your bones, that identity can survive the total replacement of its material. Keep that belief in view. It cost you nothing when the subject was atoms. The final act of this story is about what happens when the same reasoning is aimed at the audience. So pause on the summit and look back at the whole path, because you have climbed further than it felt. You began with your hand on a table and a child's question. Why is every electron exactly alike? You watched Leibniz declare perfect twins impossible, and Dehmelt's dancing patience prove them real to 12 decimal places. You listened to a phone call in which one physicist proposed that all the electrons are one electron, threading forward and backward through time, and watched the backward half of that call become the working language of particle physics, while the grand half died 3 deaths. A universe that is almost all leftover matter, electrons that are created and destroyed, entangled pairs no single traveler's diary can explain. Then the true answer stood up. One field, filling the universe, every electron a ripple on it. Wheeler's all one thing, vindicated with the geometry corrected. And just now, 2 ordinary facts, a pulse and a decade of quiet atomic turnover, showed you that the ripple picture is not exotic at all. You have been living it. Everything from here on is one question long, whether the story stops at the skin. Which would be a fine place to end if the story were only about electrons. But you have surely noticed the question standing quietly at the edge of the room for this entire journey. It walked in the moment Wheeler said, "They are all the same electron," and it has been waiting patiently ever since. If nature's answer to "Why are all electrons identical?" turned out to be "Because they are all one thing appearing many times," then what about the other perfect multiplicity in your immediate experience? What about the fact that behind 10 billion pairs of human eyes, something is looking out, and every one of those somethings calls itself I? We are going to walk to that edge, carefully, because it is the most interesting cliff in the vicinity of this physics. But I want to be honest with you before we take a single step, with a plainness the topic demands. Everything from here until I say otherwise is philosophy, not measurement. The physics of the one field is confirmed to a part in a trillion. What follows is an argument, a serious one, made by serious people with serious opposition, and no instrument on Earth can yet referee it. That distinction is the spine of everything ahead. Hold it, and nothing here will mislead you. The parallel itself was noticed by one of the founders of quantum mechanics. Erwin Schrödinger, the same Schrödinger whose equation governs the quantum world and whose boxed cat we have met in another story, spent his later years writing about consciousness, and he kept circling one observation he considered bottomless. Consciousness, he wrote, is never experienced in the plural, only in the singular. You have never experienced being 2 people. Nobody has. Wherever experience shows up, it shows up as exactly one point of view, one I, one seat at the center. 10 billion humans, and the view from inside every single one of them has the same peculiar structure, single, central, complete, calling itself me. Notice the shape of that fact. It is an identicality claim. Every instance of being someone appears to have identical form, the same first-person singularity everywhere it occurs, without exception. And Schrödinger, steeped in the physics of identical particles, drew the parallel his training suggested. Perhaps the multiplicity is apparent, not real. Perhaps, he wrote, in truth there is only one mind, appearing like the field in many places at once, each appearance convinced of its separateness. He knew exactly how it sounded, and he wrote it anyway, in books that remain in print because the argument refuses to be easily dismissed. Before the modern versions, it is worth laying out the full menu of positions,
because there are exactly 3 coherent answers to how many subjects are there, and seeing them side by side keeps the whole discussion honest. The first is the common sense view philosophers call closed individualism. There are many persons, each a separate subject, each sealed in its own life from birth to death. You are you, I am I, the walls are real. Nearly everyone holds this view without ever noticing it is a view. The second is stranger and older than it looks. Empty individualism, the position that there is no persisting subject at all, that the self is a bundle of experiences bound by memory. On this view, the you of this morning is strictly a different entity from the you of tonight, connected by resemblance and causation the way frames of a film are connected, with nothing continuous underneath. Versions of this run from ancient contemplative traditions through the Scottish philosopher David Hume to hard-nosed modern neuroscience. And the third is the one this story has been walking toward: open individualism, one subject appearing as everyone. Notice something curious about the menu. The middle option and the last option, which sound like opposites, agree on the crucial negative claim that the common sense walls between selves are not fundamental. Empty says, no self, so no walls. Open says, one self, so no walls. They differ only on what remains when the walls come down. The common sense view, meanwhile, the one everyone actually lives by, is the only one of the 3 that requires the walls to be metaphysically real, and it has proven remarkably difficult to say what exactly the walls are made of. Memory? It fades and falsifies. The body? Its atoms turn over. The brain? We will meet shortly patients in whom the brain itself was cut in 2. Every candidate wall, examined closely, goes soft. A modern philosopher, Daniel Kolak, built the third position into a full theory with a name: open individualism. His book is called, with total commitment, I Am You. The claim: what you are, most fundamentally, is not a particular body or a particular bundle of memories. Those are the ripple, not the water. The subject, the bare fact of being a point of view, may be one thing, appearing as every conscious being, the way one field appears as every electron. Kolak is candid that the view strikes nearly everyone as absurd on first contact. His project is to show it is coherent, not proven. Another philosopher, Arnold Zuboff, arrived at a similar destination by a different road. The ordinary view, you are exactly one specific person, and being you required exactly the right sperm, egg, and atoms out of astronomical alternatives, quietly commits you, he argued, to an improbability so extreme that the rival hypothesis deserves the table. That being anyone at all is what you are, and the boundaries are perspective. You already have an objection loaded, everyone does, within seconds of hearing this. If you and I are one subject, why can't you remember being me? Why, when I stub my toe, do you feel nothing? The walls between minds do not merely seem real, they seem enforced. No thought has ever leaked from one head into another. Surely that settles it. But look at how the defenders answer, because the answer is more disciplined than you expect, and it comes in 2 moves. The first move points out that the objection assumes a shared subject would have shared access, and that assumption is demonstrably false even inside a single life. You do not currently have access to your own experience of last Tuesday afternoon. You cannot feel your own childhood toothache. Under anesthesia last year, you were interrupted entirely and resumed without noticing the gap. Access to experience depends on memory, and memory is machinery. It lives in one brain and cannot consult another, the same way the file on one computer cannot be read by a machine it was never connected to. If one subject looked out through 2 heads, each head's machinery would report exactly what you observe, a single, sealed, complete feeling life with no memory of the other. The absence of leakage is not evidence against the one subject view. It is precisely what the one subject view predicts, given how brains store experience. The second move is stronger, and it should give even a committed skeptic one honest pause. Ask what evidence could distinguish the two hypotheses: many separate subjects, or one subject appearing serially and separately. Each person's experience feels singular under both. Each person lacks others' memories under both. Each person fears their own death and not strangers' deaths under both, because fear is generated by each brain's machinery about its own prospects. Run down the entire list of facts usually offered as proof of separateness, and every one of them is predicted equally by both pictures. Which lands us somewhere you have been before, less than an hour ago. Two hypotheses, identical in every observable consequence. That was exactly the status of Wheeler's one-electron universe, and there you watched physics render its verdict without mercy. A difference that makes no observable difference is not yet a scientific claim. The symmetry cuts both ways here though, and honesty insists on saying so. If no observation can distinguish one subject from many, then the many subjects view you have held since childhood is exactly as untestable as the one subject view you are being asked to entertain. Common sense is not the winner of this contest, it is the incumbent, installed by intuition, never once elected by evidence. And philosophy supplied the opposition in equal strength, which is exactly what you should demand. Derek Parfit, one of the most respected philosophers of the 20th century, spent a career arguing that questions of personal identity dissolve under pressure, and his most famous demolition tool is worth carrying with you. Imagine, he said, a person whose brain is divided and each half transplanted into a new body. A scenario surgery has already approached from a distance. Both survivors wake with the original's memories, personality, sense of self. Which one is the original? All the possible answers embarrass themselves. Both, then one person is two people. Neither, then a survivable operation somehow killed someone. Or one of them, chosen by what exactly? Parfit's conclusion was radical. The question has no answer because deep identity was never a real ingredient of the world. What matters is not some metaphysical thread of being the same one, but ordinary psychological continuity, memory linking to memory, intention to action, and that continuity comes in streams, plural, each distinct. On Parfit's picture, there is no universal subject. There are separate flowing rivers of experience, and the sense of a deep single I, anywhere, in anyone, is itself the illusion. Notice the elegance of this as an attack on open individualism. It does not argue there are many subjects rather than one. It argues the counting question was malformed from the start, that asking how many subjects is like asking how many rivers a watershed really contains. There is water flowing. The counting is convention. Galen Strawson, equally serious, attacks from the opposite flank. He is a physicalist who insists, against fashion, that conscious experience is completely real as charge or mass, and completely physical, present in matter itself. But locating experience in matter for Strawson means it is plural and distributed the way matter is, countless loci of experience, no more unified into one grand experiencer than the universe's electrons are unified into one grand particle. And there the field analogy turns and bites its own tail, because Strawson can accept every word of the physics in this video and still say, yes, one field, many ripples. And each ripple of experience is its own event. The oneness of the medium, he would insist, was never the oneness of the waves. The debate is genuine, alive, and unresolved, which is precisely what makes it worth your attention rather than your belief. I know the ground has turned abstract, so stand somewhere solid for a breath. Look at any two people, in a photograph, across a room, in your memory. The entire question of this final act is contained in the space between their eyes, whether that space is a genuine boundary in reality, like the gap between two islands with separate roots in the seafloor, or a boundary of perspective, like the gap between two waves, real at the surface, absent below. Physics answered the wave question for matter. The rest of tonight is about whether anyone can answer it for the watchers. Is there anywhere experiment touches this at all? One place, and it is the strangest bedside story in neuroscience. Beginning in the 1960s, surgeons treating catastrophic epilepsy sometimes cut the corpus callosum, the bridge of 200 million fibers connecting the brain's hemispheres. The classic results, from Roger Sperry and Michael Gazzaniga, made the textbooks. Show a word to the isolated right hemisphere and the patient says they saw nothing, while their left hand, which that silent hemisphere controls, calmly draws the object. One skull, seemingly two knowers. Gazzaniga put it with surgical bluntness. Disconnect the hemispheres on Monday, and on Tuesday the patient has two minds. For decades that was the orthodoxy. Consciousness divides when the cables are cut, and the unified self is stitched together by wiring. Then, in 2017, a team led by Jair Pinto in Amsterdam retested two long-studied split-brain patients with modern experimental care and found something that was not supposed to happen. The old results all shared a signature. Information shown to one hemisphere could only be reported by that hemisphere's own channels. Speech for the left hand for the right, which is what made two minds the natural reading. Pinto's team tested the full grid. Stimuli anywhere in the visual field, responses demanded from either hand and from speech, trial after trial. If two separate conscious agents were inside, the crossed combinations, right field stimulus, left hand answer, should collapse to guessing. They did not. Across the entire visual field, whichever channel responded, the patients performed above chance. As if perception was divided, but the perceiver, somehow, was not. One conscious agent, reporting through a split machine. Pinto said it directly. The brain, even cut in two, is still able to produce only one conscious agent, and this directly contradicts the current orthodoxy.
The counterattack came fast, from Gazzaniga's own camp, and it deserves its say. Two patients is a whisper of a sample. Both had lived for decades with their split, time enough for the brain to build subcortical back channels. And above chance is not the same as normal. The patients are strange in ways one mind does not fully capture either. All fair. The rejoinder is also fair. The original two minds orthodoxy was built on similarly tiny samples, interpreted with the confidence of its era. Which means the honest summary of the only experimental window we have is this. We cut the brain's great cable expecting consciousness to divide like everything else, and half a century later, with the same handful of patients on both sides of the argument, we genuinely cannot agree whether it did. The one place where scalpels touch the question of how many watchers there are returned an ambiguous answer. And the ambiguity itself may be the most honest data point in this entire final act. And one more clean fact belongs in the record, because it cuts against easy conclusions in both directions. Whatever is happening in those patients, none of them reports being two. No split-brain patient has ever said we. They say I, they feel single, they are surprised to learn their left hand knew something they did not. Either consciousness genuinely does not divide when the brain does, or it divides and each half is constitutionally incapable of noticing, in which case the feeling of being exactly one person is testimony no one's feeling of unity, yours included, can be trusted to certify. Sit with how strange both options are. There is no third. Before the questions everyone asks, one more thing deserves to be said about what any of this changes, practically, for the person watching. Because these positions are not just furniture for seminar rooms. The people who hold them report that holding them does something. Parfit himself left the most striking testimony in the literature. Before his arguments dissolved deep personal identity, he wrote, his own life felt like a glass tunnel. Walls he moved through faster every year, with darkness waiting at the far end. When he genuinely came to believe there was no deep further fact of being him,
only experiences, linked and flowing, he reported that the walls of the tunnel disappeared. He cared less about the difference between his own future and other people's. His death, he wrote, looked less like the end of a self and more like the end of certain connections. After it, there would still be experiences, memories carried forward in others, effects rippling outward, just none of them related to now in quite the way tonight is related to this morning. He called the change liberating and said he found he cared more, not less, about others once the wall between his interests and theirs went thin. And the open view, for its part, carries an equally concrete consequence. One Kolak states outright, "If the watcher behind every pair of eyes is one watcher, then cruelty is always, without exception, something the one does to itself, and kindness always lands on its sender." You do not have to believe either view. Tonight has given you every reason to withhold belief. But notice that the three doors are not idle. Each one, walked through sincerely, reorganizes what a person fears and how they treat the strangers on the far side of the supposed wall. Ideas about counting turn out to be ideas about conduct. That is worth knowing before you choose a door, or before you notice, years from now, that one of them quietly chose you. 3 questions always arrive at this point in the journey, and each deserves a straight answer before the ending.
First, could Wheeler's one-electron universe ever have been tested? Here is the uncomfortable truth that even its obituary deserves to record. No. Even if the tangled thread were exactly how reality worked, a universe of one knotted world line and a universe of many identical electrons would look identical in every possible experiment. The picture makes no unique prediction. Nothing observable distinguishes it. And in physics, that is its own kind of death sentence, separate from being contradicted. An idea no experiment could ever confirm or refute is not a small theory. It is not yet a theory at all. The 3 fatal blows we counted were almost a courtesy. The deeper failure is that the idea never offered the universe a chance to disagree with it. Keep that standard in your pocket. It is the sharpest tool this story hands you, and it will matter in a moment when we weigh the question about minds. Second, if my electrons are ripples of a field that outlasts every star, does some part of me persist when I die? The honest answer is deflating and worth hearing precisely. The field persists. It was there before you and remains after, and the matter that composed you persists as other arrangements. But everything you actually mean by yourself, the memories, the voice in your head, the particular pattern, is the arrangement, not the medium. A wave that disperses is not hiding in the ocean afterward. The ocean simply no longer performs it. Physics offers real continuities, but none of them is the continuity anyone is asking about, and pretending otherwise would be selling comfort the equations do not contain. Whatever consolations exist on that question live in the philosophy we just walked through, in how the counting of subjects works, not in the physics of fields. Third, why does the one field have exactly these properties, this mass, this charge, this magnetism, the same everywhere? Here, physics simply opens its hands. The field explains why all electrons match. Nothing yet explains why the template itself is what it is. The electron's mass is measured, not derived. The fine structure constant that sets the strength of the vacuum's whisper is measured, not derived. And in one of the quiet scandals of current precision physics, the world's 2 best independent measurements of that constant disagree with each other by more than either team's stated uncertainty, a standing 5 sigma splinter that limits how hard the great magnetic moment test can currently be pressed. Somebody's apparatus holds an undiscovered flaw, or the constant is stranger than believed. Either way, the deepest constants of the one field remain brute facts, taken from nature's dictation. We know the ocean is one. We do not know why it is this ocean. And now, one last uncomfortable question. The one this entire journey has been quietly building toward, and the one I cannot answer for you. We began with your hand on the table and a sameness that demanded explanation. Physics explained it. One field everywhere, and every electron a ripple of it. Then we turned to the watchers and found the same architecture staring back at us. Many minds, all running on the same machinery, each one certain it is the whole story from the inside. And there the explanation stops, because no Dehmelt has yet built a bottle that holds a point of view. So here is the question to carry out of the room. When you settled on your answer a few minutes ago, closed, empty, or open doors, what exactly did the settling? Your sense of being precisely oneself, sealed at the skin, is testimony from the only witness who could never report otherwise. A wave asserting it is not the ocean, using only the ocean's own water to say so. So which is more likely, that the feeling certifies a fact about reality, or that it is simply what any ripple would feel, whatever the truth beneath it? Notice that you cannot get outside the feeling to check. Wheeler's electron thread failed as physics because nothing could ever test it. The counting of watchers may sit in the same category, and unlike the electron question, you are not outside this experiment. You are the apparatus. So here is the full shape of what we found, gathered in one place, and notice how the pieces answer each other. A hand on a table and a sameness too perfect for coincidence. A phone call proposing the maddest possible explanation, one particle threading time. A stolen half that became bedrock, antimatter as matter running backward, drawn that way tonight on every whiteboard in the world. Three pieces of arithmetic, a 1 in a billion imbalance, particles born and destroyed, correlations no single traveler could fake, that killed the thread. And a resolution that kept the dead idea's heart while fixing its geometry. One field, everywhere, whose ripples cannot even in principle be told apart, so that the deepest sameness in nature turns out to be the signature of an underlying oneness. That much is physics, and it is as solid as anything our species knows. And then the question the physics cannot reach, standing at the edge where we leave it. Whether the other perfect sameness, the singular eye behind every pair of eyes that has ever opened, is 10 billion separate flames, or one flame, seen from inside many times. Schrödinger suspected the latter. Parfit dismantled the question itself. The split brain data cannot decide. Physics can demonstrate that all electrons are one field's excitations. It cannot say whether all experiences are one experience. That is the honest edge, and it stays open tonight. Not because the question is empty, but because nothing yet built by human hands can weigh it. If this journey gave you something worth keeping, consider subscribing. It genuinely helps these long explorations reach the kind of person who hears a 1940 phone call and needs to know how the argument ends.
One last image then to carry out of the room. Geneva, some evening in the 1960s. The lecture is over. The applause was for the man at the podium, and Ernst-Stueckelberg, who saw the backward-flowing thread first, who did the mathematics alone, in French, in wartime, unread, gathers his notes and walks out quietly with his dog, toward the lake and the sunset, needing nothing from the crowd. One man who found the truth and walked away unrecognized. One truth that outlived both its discoverers and its own first wrong guess. Wheeler asked the universe why every electron is the same, and the universe's answer, patiently extracted over 80 years, was more unifying than his wildest version. Because, underneath, it is all one thing, one field, wearing 10 to the 80th disguises, a few of which are watching this together right now. Whether the audience is also one, whether the watcher behind your eyes and the watcher behind every other pair are the same watcher wearing different evenings, the universe has, so far, declined to say. It only leaves the parallel lying there, like a thread on a table, daring someone to pull it.